All right, so going back to Wednesday we started section 4, and we were kind of talking about these sort of problems that we were running into from a perspective of classical physics. Things that we're seeing that did not quite make sense, that led us to look at the atom and our model of the atom, the Rutherford model, a little bit more closely. And so, if you recall, we ended with this concept of atomic spectroscopy, the idea that we've got these specific lines showing up when we expose atoms to energy, and it doesn't match what we think about and what we know about light. We think about light as being this continuous wave, and the spectra of these atoms aren't continuous at all. They're in fact very, very discrete. And so that raises a question for us about, well, why? And so we looked a little bit in our homework as to the why. Let's take on a little bit more evidence here as we go. Here's another kind of interesting phenomenon: black body radiation. Now, in classical mechanics, black bodies are these objects that are capable of absorbing all forms of light, which is why they're called black bodies, but also emitting all forms of light. And so the radiation that came from these black bodies, black body radiation, was expected to be continuous. But the reality of the situation was that it wasn't continuous. We weren't getting these black bodies to give out every specific idea, every specific energy. There were always breaks. And this is where Max Planck comes in. Because the idea was, okay, if we heat up a black body, the electrons inside of that black body are going to oscillate. So they're just going to kind of move back and forth and back and forth. And since there is no energy level inside of the atom, those electrons, as they're moving around, as they're oscillating, are going to just emit whatever energy they feel like based upon how much they oscillate, how much they move. Problem is, that's not what happened. And so it took Max Planck in 1900. He breaks away from this classical view of energy and says, well, hold on a second. Maybe we're thinking about this wrong. What if energy and light were not continuous when it comes to matter? What if there were these little discrete packets of energy that all energy reduced down to? Now, those discrete packets of energy were called quanta. The overall concept here is something called quantization. So that was one of your vocabulary words in the homework last night. And a couple of you messaged me, okay, I really don't understand this idea of quantization. Well, here it is again. What we're saying is that inside of the atom, it isn't the wild, wild west of electrons. Electrons aren't just free to go anywhere they want and take up any energy that they want. There are these quanta that exist, these little tiny energy steps. And since energy is a series of steps, there are only specific energies that can exist. Now, when we get to the Bohr model of the atom, we talk about energy levels. We'll talk about the fact that electrons really can only exist at certain energies in the atom, period. And in order to go from one energy level to another, it has to absorb or reflect an equal amount of energy to the jump that it's going to make. But the idea of quantization is that no, energy inside of the atom is not continuous. There isn't an infinite number of frequencies that we can get. There is very specific steps. Now, the quanta that is being described is a very small quantum of energy, 6.626 times 10 to the negative 34th joules for every hertz. So joules times seconds, that means that each hertz would carry an energy jump of 6.626 times 10 to the negative 34th joules. So that's my framework, that's my context. H here is known as Planck's constant because that is the constant, that is the quanta of energy associated with atoms here, with electrons. The problem with Max Planck is that while he had the right idea, he didn't really have a whole lot of evidence to kind of back it up. And he didn't have a way of using his equation to explain the phenomena that were taking place. It was largely theoretical. Where quanta really got its footing, however, was when it was used to explain the photoelectric effect. Now, the photoelectric effect is a rather simple experiment. We've got metal, and we're shining light on that metal. Now, depending upon the light that is being shown on that metal, one of three things happens. Either nothing happens, we get electrons jumping off of the metal, or we get electrons jumping off the metal with speed. And where quantization comes in is explaining why some kinds of light don't produce any electrons, and differing forms of light will not only produce electrons, but also produce electrons at varying speeds coming off of the metal. Albert Einstein figures it out. For figuring it out, 1905, he wins the Nobel Prize in physics. And the way he figures it out is he goes, okay, maybe Planck's got something going on. What if Planck's idea of quantization is correct? And it is the frequency of light that is driving the photoelectric effect. Why is low energy light, why is red light not able to eject photoelectrons? Maybe it doesn't have enough energy. If I use Planck's equation, I can calculate the amount of energy that is generated by that light. And if it's not high enough to get that electron out, we don't see the electron get out. Why are there varying degrees of speed afterwards? Well, now it becomes a question of momentum. If I have enough energy to get the electron out, any extra energy would be used and converted into speed. So the more extra energy is, the more quickly the electron is going to be ejected. So whereas red light maybe doesn't get electrons out at all, yellow light is able to get them out, but they kind of travel weakly. Green light gets them to be ejected, but faster, and violet light gets them to be ejected and really fast. The photoelectric effect deals with kind of a threshold speed. And we can calculate that speed based upon how much extra energy there is. And we can calculate the energy of the light based upon its frequency and multiplying that by Planck's constant. So let's take a second and just practice this calculation where we are calculating the energy of light based off of wavelength and frequency. So what we're asked here is, what is the energy of light if it has a wavelength of 640 nanometers? And then what is the energy of 1 mole of those photons? Well, to answer the first question, and to us the more important one here, we're using Planck's equation. E is equal to Planck's constant times the frequency of light. Now you'll notice here we don't have the frequency of light, we have its wavelength. Here's where that equation we were using on Wednesday comes in handy. The speed of light equation. We can use that equation to convert wavelength into frequency, and then we can plug the frequency into our energy equation. Or we're going to break out some algebra here. Remember that on Wednesday, we also rearranged this equation to convert frequency out of wavelength. Well, if we do that and substitute into our original equation, we get the best of both worlds without having to do 2 separate equations. So this is the Planck equation, now modified for wavelength instead of frequency, and it's perfectly valid to use in this form. So Planck's constant, 6.626 times 10 to the negative 34th joules times seconds, multiplied by the speed of light, 2.998 times 10 to the 8th meters per second, over the wavelength, 640 nanometers. And just remember our trick from Wednesday, to turn the nanometers into meters, just take that value and multiply it by the conversion factor, 10 to the negative 9th. If I follow this calculation all the way through, 6.626 times 10 to the negative 34th, multiplied by the speed of light, divided by 640 times 10 to the negative 9th, to 3 significant figures. And the reason we're saying 3 is because they're telling us that 640 is actually 6.4 times 10 to the second. So 3 digits in that measurement. We get 3.10 times 10 to the negative 19th joules. And the joules there coming from seconds canceling and meters canceling, all that's left are those joules. Now, this is the number of joules in a single photon. So 1 particle of light. To figure out the energy of 1 mole of those photons, well, we're going from the microscopic world to moles. We're going to need to multiply by Avogadro's number. So photons cancel out. Multiply our number by Avogadro's number. Again, to 3 significant figures, 187,000 joules for every mole. So even though we're not talking about a very energetic form of visible light, we're still talking about a decent amount of energy in a mole of those photons. You know, this is 187 kilojoules. All right, so the question after this is one of your homework assignment questions. So we're gonna skip it for now. But just understand that this question here is of the same kind of question. We're asked to take a wavelength and turn it into energy, just with a different energy. So it's there, but again, we're gonna skip over it because I want to make sure that we get a chance to talk about the Bohr model here, because the Bohr model really is kind of the essential stuff for this weekend's assignment. So what the Bohr model of the atom does is it takes that concept of quantization, the idea that energy is in these steps, and takes it kind of to the nth degree. So not only is energy quantized, but in an atom, it's really quantized. There are very specific amounts of energy that are allowed inside of the atom. We call those specific energies energy levels. And those energy levels in the Bohr model of the atom extend circularly from the nucleus, kind of like planets around our sun. And so the Bohr model of the atom is sometimes referred to as the planetary model of the atom. And we can see from this diagram exactly why that is the case. The electrons are the planets, and the orbits are the energy levels are the orbits that those planets go on. And from this Bohr model of the atom, we can start to see that if we think about these rings as actual energy, we can start to understand why those spectral lines exist the way that they do. Because if this has a particular energy and this has a particular energy, then moving from one ring to the next can only involve a certain amount of energy. And since energy is directly related to wavelength and frequency based on the Planck equation, that's why we only get a very specific wavelength in those spectra. So it follows very closely from that idea. Now, Bohr introduced an energy calculation for the energy difference between his energy levels. Notice that the energy, the relationship here is very similar to that Rydberg equation that we used and saw at the end of Wednesday's lecture. The only difference is the value of our R is different. And that's because R is equating joules instead of meters. Remember, the equation that we used, that we saw at the end of Wednesday, was all about finding the wavelength of light associated with that energy transition. Here we're talking about the energy of the light associated with the transition. And the important thing to draw out of this is that this sign does make a difference in terms of how we interpret that data. So when delta E is positive, that means that energy is going in. And we see this happening in the form of what we call excitation. The electron gets excited. When electrons get excited, just like when people get excited, they start to go up. They go up in energy level. Now, that higher energy state, that excited state, is not a stable one. Eventually, that electron is going to have to come back down to where it started. Now, where it started is called the ground state. The ground state is kind of that lowest energy configuration. When an electron goes down in energy, this calculation is going to give us a negative number. And this ultimately is the difference between the emission spectra, the bright line spectra that you saw in the homework, and the dark line spectra, the absorption spectra that you saw in the homework. So why were those values the same? Why do the bright lines match the dark lines? Because the energies are the same. It takes just as much energy to go up as it does to come back down. And since energy is related to frequency and wavelength, the two are exactly the same. And so that's where we're going to stop for today and for this week. Just again, seeing how that relates back to those lines. And so on your way out, again, 2 calculation questions here covered in the video. On your way out, hit this last question so that you get your participation point for today, and have a great weekend.